Hello, this is Mrs. Scarpel, and this is the first video for the first lesson from Unit 2 titled Transformations Shifty Wise. In this particular lesson, we're going to be finding patterns in the equations and graphs of quadratic functions. The question we'll be able to answer at the end of this lesson is what happens to the graph of f of x equals x squared when the equation is changed by adding, subtracting, or multiplying by a constant. So throughout this lesson, we refer to Optima Prime, who is designing a robot quilt for her new grandson. She plans for the robot to have a square face. The amount of fabric that she needs for the face will depend on the area of the face. So Optima decides to model the area of the robot's face mathematically. She knows that the area of a square with side length units, which can be inches or centimeters, is modeled by the function a of x equals x squared square units. So if you remember that the area of a rectangle is length times width, and that the sides of a square are all the same, that is why we get x squared, because we would have x times x. Now, in this context where we're measuring fabric, what is the domain? Can you have negative values in your domain? Remember, domain is the set of x values. And no, we can't have negative values when we measure something. So our domain is going to start at 0. And it can increase up to infinity, because we're not sure what her maximum size is that she can have. So those side measurements can be anywhere from 0 to infinity. Here we're going to match some other area equations with these statements about how the area is changed. So just keeping in mind that area equals x squared we're going to write this again, and I'm actually going to try typing it. Area equals x squared is what we are working with. So when we have the length of each side is increased by 5 units, remember that x in the x squared is a side length. So if we are increasing a side by 5 units, that means we're increasing the x by 5 units. So if we look at these equations, the first one is 5 times x squared. The second one is x plus 5 squared. The third one is 5x squared. And the last one is x squared plus 5. So we want the length, which is x, increased by 5 units. Hopefully you recognize that that will be equation number 2. Then we have the length of each side is multiplied by 5 units. The difference between 1 and 3 is that on number 1, we're taking x squared times the 5. Order of operations say you do exponents first. 3, we're going to multiply 5 with x and then square it. So our best option for this statement is number 3. The area of a square is increased by 5 square units. We know from our equation that the area is a equals x squared. We're increasing the x squared by 5 square units. That's going to be equation number 4. And then finally, D, the area of a square is multiplied by 5. The only equation that's left is number 1. After thinking about those equations and thinking about her domain, Optima started thinking about the graph of y equals x squared in the domain of all real numbers. And the reason this is important is because we're going to do a full graph for a full quadratic. In Unit 1, a lot of our quadratic graphs were just half of a parabola. In this particular lesson, we're focusing on the entire parabola. So our first job is to make a table that contains both negative and positive values of x and graph the function. So my table is going to have x, an x column, and a y equals x squared column. And we're going to use the values -3, -2, -1, 0, 1, and 2 for our table. So to find the value when x is -3, we have to do -3 squared. -3 squared is 9. Then we have -2 squared. -2 squared is 4. -1 squared is 1. 0 squared is 0. And then we have +1 squared is 1. And +2 squared is 4. So we now have our table using both negative and positive values of x. So if we plot these points, well, first, before I plot the points, I need to make sure I have my axes on my graph. So the horizontal is x, the vertical is y, and then I'm going to plot the points. So -3, 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, 9. -2, 4. 1, 2, 3, 4. And I know we're not seeing the line for 1 here, and I apologize for that. -1, 1. 0, 0. +1, 1. +2, 4. +3, 9. And then we have our parabola that goes through it. It's always easier for me to try to get that bottom curve in first. And it's going to extend, and then I'll come down the other way. Oops, kind of missed my points there. Let's try that again. There we go. And this is the graph of y equals x squared. So what are some of the features that you notice? Some things that were mentioned in class was that we have a vertex at 0, 0. It has a minimum. The graph is a parabola, and it is symmetrical. And I think I have too many m's in symmetrical. There we go. Now, it's symmetrical around the y-axis. And we have a name for that line of symmetry. This line that I've just highlighted in pink is called the axis of symmetry. Oh, we should put that in a darker color so you can read that. Well, I guess symmetry should have two m's now that I see it there, so let's put one back over here. And in this case, the axis of symmetry has the equation x equals 0. The equation of any vertical line is x equals. So if this axis of symmetry were to be anywhere else, we would say x equals and then whatever the x value is for any point on that line. So now let's practice some things. Optima began wondering about how changes to the equation of the function, like adding or multiplying by 5, affect the graph. She decided to make predictions about the effects and then check them out. Make your own predictions of how the graphs of each of the following equations will be the same or different from the graph of y equals x squared. And you can pause the video at this time if you want to take some time and write down your own predictions. So our first thing we're going to test is just adding 5 to x squared. What if we add 5 to what was the area before? So what Optima did was she graphed it along with y equals x squared in the same window. So in class, we used the calculators and we graphed both y equals x squared and y equals x squared plus 5 in the graphing calculator. We know from the previous example that this is what y equals x squared should look like. The blue graph here is y equals x squared plus 5. And let me label that. I guess I need to type it. Again, that blue curve is the equation for y equals x squared plus 5. So how is it different from the original y equals x squared? Students pointed out, well, that some called it the starting point, some called it the vertex. The correct name for this point is that it is 5 units above y equals x squared. So let's take a look at a couple of others. So Optima, knowing that things make a lot more sense with more representations, tried a few more examples. She tried y equals x squared plus 2 and y equals x squared minus 3, looking at both a table and a graph for each. So here was her result. The blue curve is for x squared plus 2. And I'm going to put together a table here for y equals x squared plus 2. And still using the values -3. And we notice here that when it's -3, we're not even on the graph anymore. So the table, when it was -3, had 11. -2 had 6. -1 We can even look at it. Negative 1 here is up 1, 2, 3. 0 was at 2. 1 was back up to 3. 2 was back up to 6. And 3 was back up to 11. The table for the green curve and the graph for the green curve is for the equation y equals x squared minus 3. So creating my table again. Using negative 3 up to positive 3. So at negative 3, I believe we should be able to count this one. We are at 6. Negative 2, if we look at the graph, negative 2 is at 1. Negative 1 is at negative 2. 0 is at negative 3. 1 is back up to negative 2. 2 is back up to positive 1. And 3 is back up to 6. So, what are some conclusions that you would draw about the effect of adding or subtracting a number to y equals x squared? This is what we decided in class. When adding to x squared, the graph shifts upward. When subtracting from x squared, the graph shifts downward. So when we had the plus behind the x squared, we went up 2 units. When we had the minus behind x squared, we went down 3 units. And then Optima decided she wanted to try, what if I add or subtract from the x before I square it? And I created the two equations we would use, y equals x squared, or x plus 3 squared, and y equals x minus 2 squared. Again, we compared the graphs with the original y equals x squared. And you'll see that we have a blue graph that looks to be 3 units to the left, and a green graph that appears to be 2 units to the right. This x plus 3 squared is that blue curve, where that x is negative 3. And our table looks like this. So x parentheses, x plus 3 squared. Our vertex is at negative 3, so if I went 3 numbers to the left of that, that would put me at negative 6. Has the y value of 9, like our original. Negative 5 has the value of 4, like the original. Negative 4 has the value of 1, like the original graph. And then negative 3, we are on the x-axis, so our y value is 0, just like our vertex y value is 0. Negative 2 goes back up to 1. Negative 1 is back up to 4. And then 0 is back up to 9. X minus 2 squared is the green curve. Its table looks like this. So our vertex is at an x value of 2. So 3 to the left of that is going to put us at -1, was up at 9. 0 is at 4. 1 is at 1. 2 has a y value of 0. 3 went back up to a y value of 1. 4 went back up to a y value of 4. And 5 went back up to a y value of 9. So I've created each of these tables so that we have our vertex point illustrated in the middle of the table. So we have -3, 0, and we have 2, 0. Those are both our vertices. The thing they have in common is that y is 0 for each of them. So what can we conclude when we are adding before we square? Well, when we added the 3, the graph went to the left. So we can say when adding to x, the graph shifts to the left. When subtracting from x, the graph shifts to the right, which seems a little counterintuitive. Usually if you see something +3, you want to go more. You want to move to the right. And when you see a -2, you want to move to the left. So why is it that they're shifting opposite of what you might think when you first look at the problem? Well, remember how I pointed out that the vertex for each of them has a y value of 0? What value would I have to plug in for x so that this equation equals 0? It's -3. In the second equation, what would I have to substitute for x so that this expression equals 0? It would have to be the +2. That's why the shift happens the way it does. So in class, the students were given some time to think about it, and the response was the expression needs to equal 0 to find the vertex. And I'll change this to black to make it easier to read. That was what we came up with. One last thing to be looking at. Optima thought that problem 7 was very tricky and had hoped that multiplication was going to be more straightforward. So she decided to start simple and multiply by -1. So she began with the graph of y equals -x squared. If you'd like to pause the video so you can think about what might happen, go ahead. When Optima graphed this, and when we graphed this in class actually, what we found was a parabola that was upside down, or the reflection of y equals x squared. So why does it have this effect? It's because the negative is changing the value of every single y value of the original equation. The negative in front changes the y value for every x value to a negative, which is going to be below the x-axis. So after we looked at what just adding a negative does to it, we looked at, well, what happens when we change the multiplier? A, what if we change that value? So we did one with a -2, and we did one with a +1/2. Now because of the negative on the -2, we know it should reflect downward. Our y values will be negative. So keep that in mind as I reveal the graphs here. I have a blue graph for that first equation that is reflected downward, but if you compare its shape to the original, it's a little bit narrower. We call this a stretch. And when we have the green graph for the second equation, it's wider than the original. We call this a shrink because the y values are less than what the originals were. So just to show you what the tables are like, for the first one, if I were to be able to plot -3, and we were able to look at a table on our calculators, we would see that it's at -18. -2, we can see this on here, is at -8, I believe. 1, 2, 3, 4, 5, 6, 7, yeah, 8. So -2 is at -8. -1 is at -2. 0 is at 0, so the vertex didn't change. 1 is back down at -2. 2 is back down to -8. And 3 would have been back down to -18 if it appeared on our graph. For y equals 1/2 x squared, I'm going to put my 1/2 in parentheses just like we had to do for the calculator. And that's so that the calculator knows that we are multiplying by 1/2 after we square the x, and that we're not taking 2 times x squared and then dividing 1 by that answer. So at -3, we are actually somewhere between 4 and 5. It's 4.5 actually. At -2, we are at 2. At -1, we are at 0.5. And 0 is at 0, 0. So when we multiply, it doesn't change the location of the vertex. 1 is back up to 0.5. 2 is back up to 2. And 3 is back up to 4.5. So, some things we concluded. When the multiplier is larger than a, or is larger than 1, and that's the a, the graph stretches. It gets narrower. When the multiplier is less than 1, and again that's that value of a, the graph shrinks. or gets wider. So those are the transformations we explored with our quadratic function and our basic quadratic function of y equals x squared.